Hello and welcome to lesson 3.2, integrals as net change. Today we're going to see how we can use integrals to actually calculate both displacement, distance, total distance traveled, things like this, and also use it in calculating other aspects. So, first off, linear motion of an object along a line, horizontal axis, can be described using velocity function. Positive velocity denotes moving in the positive direction, usually right, and the negative velocity denotes moving in the negative direction, which is usually left. Remember that you can list displacement as velocity times time. So distance equals speed times time is another object that's similar. Given a velocity graph, we can determine displacement from t equals a to t equals b by calculating the net area between the velocity curve and the time axis. So in other words, we're calculating the integral of v of t dt. This means that we can use we can find the object's position at a certain time by adding the displacement to the initial position, meaning we can get this formula. So s at some value b is given by s at some value a plus the integral from a to b of v of t dt. Or if you want, you can replace the a with the 0 if you're looking at initial values starting at no time. And total distance is the absolute value of the function. Now you can use the absolute value function either on the graphic calculator and or by calculating the area underneath the curve just by determining where it changes from negative to positive. So let's start and look at this function right here. This is our velocity function. V of t equals 1/3 t cubed minus t squared. Let's start up by looking at this function. Just remember that this function, you can factor out a t squared. You get 1/3 t minus 1. That means your values when this is equal to 0 is t equal to 0 and t equal to 3. So this is probably going to look like a function. I'm going to just draw a little sketch of this thing. Because I know it's cubic, it's got to look something like this kind of shape. It's hitting 0 and it's hitting 3. So to start out with, the velocity is going to be negative from 0 onwards to 3, and upwards of 3 it's going to be positive. So now we know where it's negative and where it's positive. So to start out, calculate this. And also we notice the object's initial position at 0 seconds is 5 meters. Okay, so determine its displacement over the first 4 seconds. So in other words, we're looking for integral from 0 to 4 of 1/3 t cubed minus t squared dt. Again, you can use your graphic calculator functions to calculate this, or you can do it manually. I'm going to try this one manually. So my antiderivative of this one would be 1/12 t to the 4 minus 1/3 t cubed, going from 0 to 4. So that means I've got to substitute the value 4 in the function. I also got to subtract that from 0, because if I substitute 0 in, it's going to equal 0. Use my calculator, and I found out this is 0 meters. So at 4 seconds, we've traveled the same amount of distance that we traveled from 0 to 3, and then 3 to 4. So it's basically hasn't moved, but has gone back and forth, if you wish. Just determine its position after 6 seconds. So if we want to find its position after 6 seconds, we're looking at s at 6, and we're looking at s at 0, plus the integral from 0 to 6 of v of t dt. Okay, so this is going to be the value 5, because we know that was the original value at the beginning. I again, we're going to use our antiderivative that we used from before. Because I know what it is, I'm just going to place it in here. This going from 0 to 6. Okay, so now 1 over 12, 6 to the 4, minus 1/3, 6 cubed. Again, I gotta subtract 0 because I'm subtracting if it was substituted as 0. Use my calculator, and I find out we've traveled a total of 41 meters. Don't forget to include the units. Okay, so this next one. Let's try this next one. Total distance traveled of the first 5 seconds. So in order to find the total distance traveled, you're looking at the integral from 0 to 5 of the v of t in the absolute function dt. So again, we could use graphing calculator, or we could do this manually. If we do this manually, remember we're going the same antiderivative for each one of these is the same thing. But here, I'm going to have to go from 0 to 3 to begin with. And then I'm going to have to put absolute value signs on this. Then I'm going to have to add 1/12 t to the 4 minus 1/3 t cubed from 3 to 5. Because I know at 3 is where it changes in size. Okay, so if I use my calculator, I found out this is 2.25, a negative, so I'm going to have to put absolute value signs on this. That means that value there. Now I'm going to find out this value. This is going to be, hold on a second. Okay. This is going to be 10.417. Then I have to subtract negative 2.25 from this, and then I get this value as approximately 14.917 meters traveled. Again, I can use the absolute value sign on my function, or on my graphic calculator, to calculate this as well. Okay, last part of this question. Determine the average velocity of the first 10 seconds. Since we're looking for average velocity, we're looking for 1 over 10 for the integral from 0 to 10 of the same function that we've been finding already. So 1/3 t cubed minus t squared dt. Again, I can do this manually since I know what the antiderivative is for each of these. It's always the same. We're going from 0 to 10. Okay. So now we substitute the value 10 in. And I get this is the value 50. Now this is average velocity, so average velocity would be meters per second. Remember, this value right here is in meters. This value is seconds, so it's meters per second. And there we go. Okay, so if we didn't actually know the information here about the function, we can use trapezoids to calculate the area or the approximate area underneath the curve. And that's how sometimes some functions operate. They don't give you all the information available, it just gives you information at specific times. So what you can do is you can create a couple various different trapezoids. So this is called the trapezoidal rule. So let's say you do have some area underneath the curve up to, let's say, going from y0 to y4 at these values here. Well, what you can do is you can create trapezoids. Well, a trapezoid just calculates the area underneath the curve by adding these lengths right here, multiplying by the distance, multiplying by the distance here, and dividing by 2. Now you can keep doing this by adding a couple of other ones. And you just keep adding your trapezoids until you run out of trapezoids that you have. So hopefully you can see the pattern developing here. Now sometimes, not always, but sometimes, these h values turn out to be the exact same size. Now if the h values turn out to be the exact same size, this area that you have here, we'll call it A, can be calculated just by factoring out the value of h and 2, which you can factor out the half, by the way, at any point in time. And then you have y0. You actually have two y1s. You have two y2s. You have two y3s. And you have just one y4. And then you can calculate this a little faster, a little easier, only if these values of h are all the same size. So let's take a look at our last example. So the following table shows the number of houses sold per month every 4 months since January 2015 in a town. So we want to estimate how many houses were sold in 2015 based on this chart. And as you can see, it's only given it as specific values, so it doesn't give it to us as a function. So we're going to have to use our trapezoidal rule. So the total number of houses, we'll call it T in this case. I start with, now notice they're all 4 months apart. If they're all 4 months apart, what you can do is you take a 4 over 2, factor it out. Now the first time it happens, it's 0. The next time, you have the value of 27. That value is going to be added twice. This 36 is going to be added twice. And the value of 32 only once. Now if you want, you can separate this again into multiple pieces. So if you wanted to, you could write this as 0 plus 27 times 4 over 2 plus 27 plus 36 over 2 times 4 plus 36 plus 32 over 4 over 2 as another option. If you work this out, well, this value just turns out to be 54. This one turns out to be 126. The last one turns out to be 136. We add up all these. This turns out to be 316. So there are 316 homes approximately being sold in the year of 2015. And thus concludes this lesson.